So good evening all. So today we will see the problem solving session 3 on topic drying operations. So here is a brief recap, physical mechanism of drying, then drying equilibria, then important definition and terms, then the drying rate curve, then calculation of the drying time from the drying rate data. So first, what is the drying? So drying is a process, is an operation in which the liquid, generally water, represent in a wet solid, is removed by the vaporization to get the relatively liquid free solid products. So drying does not demand or ensure the complete removal of the moistures. So I read that the various pro, pro means that various process involve means drying involved in the various process here. So here is a in a foodstuffs user drying operations. So first we will see the mechanisms. So drying is governed by the principle of the transport and heat mass. So and moisture can be moved within the solid by the variety of mechanism depending upon the nature and type of the solid and its state of the aggregations. The solid like crystalline granules, beads, so this is the types of the solid. Then powder, sheets, slabs, filter, cake, and etc. So here is a the principle is means heat and mass transfers. Here is a convection heat transfers, and here is a mass transfer. So means here is a air inlet high temperature, and in the solid has a low temperature. So it transfer from air to the solid product, and here is a where moisture removed from the solid with the help of heatings. So here is a mass transfer. So here is a both the heat and mass transfer uh, occurred in the drying process. So based on that, question per one, drying involves the transfer options. Option given heat, mass and heat. So see, mass and heat. Okay, Mohsin. Mohsin, am I audible?
Yeah, yes, sir.
Okay. Have confirmation because they initially no one joined, so for that time. ठीक. So next is the movement of the moisture within the solids. So so there are the different movement in the moisture in the solids like liquid depositions, then capillary movement. The capillary movement meant like here is a mm, the moisture passes through the narrow pathway. It's on without help of the gravity. Like here is a surface like so moisture transfer in a narrow path without helping the any external force. For example, gravity. So that's the capillary movement. And the next is a constant drying rate period, and then the vapor depositions. So here is the graph show the drying rate versus the moisture. So we'll see the details of these graphs in the next slide. Next or yes, next slide. So here say here's a mechanism of moisture transfer in a different solid, liquid diffusions, and then transfer by the capillary force, then pressure induced transport, and vapor diffusion transport. So like here is the solid materials, here is the moisture, right? when we heating at particular temperatures, right? So drying can be possible by the providing the hot water to the solid surface, or it can provide by with the help of the medium, like for example heating and like vacuum oven and like such that. So initially the uh, moisture transfer in a in the liquid diffusion way, like after that the capillary force. So so moisture transfer in the capillary actions, and then pressure induced transfer means when we provide the uh, hot air with a high flow rates. So it's a pressure induced transport, and vapor deposited at the end. Initially the vapor goes to the environment. So initially last at the end process the vapor deposition happened in a solid surface. Next is the mechanism that dominates depend on the nature of the solid, its pore structure and rate of drying. So in granular and porous solids, capillary phenomena happens, means transport of the moistures. Porous and non-uniform, big and small liquid diffusions. Then solid shrinkage on drying, compressive force to squeeze out the moisture, pressure induced transfer of the liquid within the solid. And at a low pressure content, vaporization occur below the surface. Vapor has to be diffused out of the solid, right? Next is the drying equilibria. So the drying equilibria is the relation between the moisture content of the solid and the humidity of the ambient drying medium at a equilibrium, right? So drying, the loss of the moisture by the vaporization occur till the moisture content of the solid is more than equilibrium value under the prevailing state of the ambient medium. So here is a graph show the relative humidity versus equilibrium moisture content. So for a non-hydroscopic, non-hydroscopic means which repel the waters. So it is a abstract fibers is a non-hydroscopic. So it has a equilibrium moisture content is a zero. But for a hydroscopic component, the equilibrium moisture content is a higher. Like for example, is a 7. So it's a 0.3. 7 is a potato. So around the 0.3 equilibrium moisture content. The moisture present in the solid exerts the pressure which is equal to or less than the vapor pressure of the water at a particular temperatures. So based on that, like pressure equal to or less than, so that's the moisture uh, have a particular term. So we will see on the next slide. So it all depend on the nature of the solid, moisture content and a temperature, right? The solid and gas are in the equilibrium. The moisture content of the solid is equilibrium moisture content at the operating conditions. So here is a definition of terms. The moisture content on a weight basis. So it expressed in the mass ratio unit. So moisture content equal to 1 kg of moisture divided by 1 kg of dry solid plus x kg moisture into 100 equal to x. So here is a 1 kg of moisture is you can say x. So 100 x into 100 divided by 1 plus x. This is a this is on a weight basis. And moisture content on a dry basis uh, is a kg of moisture divided by kg of the dry solid. So here it's a 100, it's a x 100. So here is a graph relative humidity versus x. So first a bound moisture. The amount of moisture is a solid that exerts the vapor pressure less than that of pure water at a given temperature. It called the bound moistures. Like the vapor pressure of solid. Sorry. the amount of moisture, okay, vapor pressure of the moisture on the solid is less than pure water. Means vapor pressure of the pure water at a given temperature is called the bound moisture. Regulating vapor pressure of moisture is less than vapor pressure of water at given temperatures. That's called the bound moisture. And unbounded moisture, the amount of moisture in a wet solid is in a excess of bound moisture is called the unbound moisture. So here is the excess of bound moisture, that's called the unbound moisture. So it is a exert vapor pressure equal to that of the water. So here in that conditions, vapor pressure Vp of moisture equal to Vp of water. So total moisture denoted by the X is a bound moisture plus unbound moisture. This ones, this plus this. This is a total moisture. Next is the equilibrium moisture. The moisture contained in a solid that can remain in a equilibrium with a drying medium of a given relative humidity at a given temperature. Here is a equilibrium moisture. These ones. So after that, there will be no changes in the moisture content of the solids. That's the equilibrium moisture. The free moisture, the moisture in a wet solid in excess of the equilibrium moisture is a free moisture here. After that, the whatever the moisture removed from that's the free moisture. So here the only free moisture can be removed by the drying under the specified conditions. Below equilibrium, so we cannot remove the moisture from the solid. So total moisture is X equal to equilibrium moisture plus free moisture. Getting or not?
Yes, sir.
So based on the drying equilibrium, some definition and terms and this ones. So the MCQ. Here is a statement. Can the moisture content of solid dry basis to be above 100%? You have to tell the answer just. So we see the just term now here. The moisture content in dry basis is kg of moisture divided by kg of dried, right? So can a moisture content of a solid dry basis be above 100%? Option given here. You have to just answer. You have to say yes or no or both.
No. Answer B.
No, no. Just use the concept. Just I recently just I terms I explained. Moisture content in a dry basis is a kg of moisture, kg of dry solid, right? This is a moisture content in a dry basis. This is a moisture content, right? So suppose you have a 1 kg of dry solid. You have 1 kg of dry solid, and 1.5 kg of water of moisture. So here is a 1.5 divided by 1 into 100. So it's a 150 degrees Celsius, right? So moisture of solid it can above the 100%. Clear or not?
Oh, okay, sir. It's clear.
Question 3. Which of the following is probable value of equilibrium moisture of a sand at 40 degrees Celsius, 70% relative humidity of a ambient air? Here is asked the equilibrium moisture. So here is a graph. This one's. This asked right here. So here asked the probable value of the equilibrium moisture of sand at 40 degrees Celsius, 70% relative humidity. So first go to the options. First A. A means a higher, means is a highest value of the moisture. So it is not possible as a equilibrium. And 0 means, so it is also not is a unrealistic value, because any solid have a some equilibrium moisture content. So here is the 0 not possible, right? So 0.3 kg of moisture per kg of dry sand. So this is a possible probable value of equilibrium moisture of sand. Clear or not? Because here is a relative humidity. So it is 0 to 1, right? So here like uh, mm, so this find the equilibrium moisture, like X star. So equilibrium moisture denoted by the X with a superscript star. So one is not possible because it's a means higher higher value for the moisture, but it is not uh, uh, equilibrium moisture, and 0 is not possible. So it's a below equilibrium. The probability of is less than the equilibrium moisture contents. So it's a C possible. Clear or not?
Yes, sir.
Now we have to tell the answer. Question number 4. Here is a graph given. The moisture in the solid after the attaining the equilibrium is known as.
It's answer A, bond moisture.
No. Just read the question. Read the carefully. The moisture in the solid after attaining the equilibrium is known as.
Equilibrium moisture.
Yeah, right. It's the equilibrium moisture. Which of the following best describe the bound moisture in a drying operations? In a bound moisture in a drying operations. So option given: moisture that can be removed easily by air drying, and moisture that is chemically bonded with the chemical within the material structure. The option C: moisture that exists in equilibrium with the surrounding airs. This is not possible, right? The moisture that remains after the material reaches its equilibrium moisture content. No, this is wrong. Moisture that can be removed easily by the air drying. So in the bound moisture, this is cannot possible because initially it can possible. So an option B is match moisture that is chemically bonded within the material structure. Question number 6: which of the following defines the term of critical moisture contents? So here is the option given. Try to tell the answers. First read the carefully the options and tell the answer. Here is a graph given. The option A, the moisture content at which the drying rate is begins to decrease. The moisture content at which the material is completely dry. C, the option content at which bound moisture start to evaporate. And the moisture content at B, the moisture content at which the material can no longer absorb the moisture from the environment. So here is a critical moisture. This one you can say XC. So after that, here the critical moisture content. So here the drying rate. The drying rate here is the drying rate and is decreased. So you can look the in option the moisture content at which the drying rate begins to decrease. Like this is math. So option B the content. This is not all because and see the moisture content at which the mountain might start to evaporate. No, this is the initial conditions, and the moisture content at which the material can no longer absorb the moisture from the environment. This is not right. Question 7. If the initial moisture content of a material is 50% and the critical moisture content is at 20%. So here is a Xi given 50% and critical moisture Xc. So critical moisture denoted by Xc, the initial Xi. Which of the following represent the removal of the unbound moisture? This one. So here initial condition given 50% and critical moisture content 20%. So which of the following represent the removal of the unbound moisture? So based on that we have to select the options. Here given the four options like remove moisture from 50% to 30%, 50% to 20%, 50% to 10%, and 20% to 10%. Did you understand the problems? Mohsin, am I audible? Mohsin, am I audible? So here the option is given remove moisture from the 50 to 30%. So this involves the removal of some of unbound moisture, but not all, right? Because the critical moisture content are 20%. So this is not the solution of these questions. The B, the remove the moisture from 50% to 20%. So in this involves all the unbound moistures and the reach the critical moisture content. So this is the matchings. And option C, 50 to 10%. So this is going behind the critical moisture contents. No. And option D, remove moisture from 20 to 10%. So this involves the only the bound moistures. So this is no. So option B is right. All of you got clear? Next is the drying rate curve. So batch drying, the constant drying conditions. The time required for the drying of moist solid to the final moisture content can be determined from the knowledge of the rate of drying under the given operating conditions. So drying rate is a function of the temperature, humidity, flow rate, transport reservoir properties like Reynolds numbers, Commit numbers. So here is a graph moisture content versus T. So here initially we hitting so moisture the how means the we can explain the how moisture is removed from the solid. So initially A to B, B to C, C to D, and D to E. So here A to B is the outbound moistures, then B to C is the constant drying rate, and C to D the first falling rate, then D to E second falling rate. So later SA is the mass of bone dry of solid, A is the drying area, X is the moisture content at any times. So rate of drying in kg moisture per meter square second equal to Na is equal to minus S with a subscript S divided by A into dx dt approximately minus S with S with a subscript S divided by into delta X divided by delta T. So here is a negative sign is used to say, moisture content decrease with the time. The plot of drying rate N versus moisture content X is called the drying rate curve. So here is a drying rate divided by drying rate versus X. So here AB is the drying of solid accompanied by the release of the moistures, right? And B to C are the constant rate period. So dx here dx by dt equal to constant. And CD and DE the falling rate period, right? The equilibrium moisture content X star here is a reach at a point E, after which the curve become flat, indicating no further loss of the moisture. That's the equilibrium moisture. So here is the constant rate period, here is a falling rate period. So over the region B to C, the drying rate remained the constant at a NC. So NT is equal to KY mass transfer coefficient into humidity at saturation conditions and humidity at initial conditions. The moisture content at point C where the constant rate period terminates is called a critical moisture content. So this moisture content called is a critical moisture content. And CD represent the first falling rate period and DE is a second falling rate period. Next, mechanism of moisture transport. The first, the constant rate period. The surface of the solid remain uniformly moist due to the rapid transport of the moisture from the inside to surface. Virtually, there is no resistance to the liquid transfer within the solid. At the end of the period, the dry patches appear on the surface. Yeah. In the first falling rate period, C to D, the unsaturated surface drying occurs. So drying rate is governed by the combined transport resistance of moisture inside to that of the outside solid. The transport by the capillary force and the liquid diffusions. So here is a two means the mechanism of transport of the moisture inside the surface. In a second falling period, the moisture content become a quite low. So internal diffusions of moisture essentially controls. So here is a XC critical moisture content of wet solid is not a constant quantity. So it is depend on the pore structure of the particle size of the solid, thickness of the weight solid, and drying rate, which is the function of the temperature, humidity, then the Reynolds number, commit numbers. So here is a uh, in a falling rate period. So the moisture transport, the the mechanism of moisture transport is the internal diffusions, then capillary force, and the liquid diffusions. So based on the drying rate curve, so here is the problems, MCQ questions. Which of the following statement is true about the constant rate period in a drying? Option A, given the surface of the material remain wet and temperature remain constant. Right. The option B, the surface of the material become a dry and temperature increase. Internal moisture diffusion control the drying rate. And the option D, the drying rate continuously decrease. So this is not, because at this condition is a constant rate. So material remains wet and temperature remain a constant. So option A is correct. In a question 9, in the drying rate curve, what does the first falling rate period represent? The option given, the period where surface evaporation is only the mechanism. No, this is not possible here. The period where internal diffusion of the moisture becomes significant. This may be possible. Option C, the period where the drying rate is the highest. No, the highest rate is in a constant rate period. And option D, the period where the material temperature is decreasing. No, this is not possible. So option B is correct. The period where the internal diffusion of moisture become significant. Question 10. What typically marks the end of the constant rate period in the drying rate curve? What typically marks the end of the constant rate period in the drying rate curve? When the surface moisture start to decrease significantly. So this may be possible when the internal moisture content reach equilibrium. No, this is not possible here. When the temperature of drying air decreases, no, because at the drying rate period, so temperature is a constant. When the relative humidity of drying rate increase, no. So here should be the measure relative humidity also same. So option is a right. The surface of moisture start to decrease significantly here. Question 11. Which factor does not significantly affect the drying rate during the constant rate period? Here is a ask, does not significantly affect, right? So here is a air velocity also affect, surface area of material also affect, air temperature also affect. So material thickness is a no, means the not a significantly affect the drying rate during the constant rate period. So option D is correct. Question till during which period is the rate of drying mainly controlled by the movement of the moistures within the material? So initial warming, this is not possible. The constant rate period, no. In first falling rate period, here is a capillary force and liquid diffusions. Second falling rate period is possible because this controlled by the movement of the moistures, means internal diffusions. Option D is correct. Question number 13. What characterize the second falling rate period in the drying rate curve? The drying rate is constant, not here is a drying rate is the decreasing in falling second falling period. This is not possible. So drying rate in decrease due to the decrease in the surface moisture. So this may be possible. The option C, the drying rate decrease due to the difficulty of moisture movement within the materials. The drying rate increase due to the increase in the temperatures. So here is the option C is correct. So drying rate decreases due to difficulty of the moisture movement within the materials. So this is not possible. This one. Question number 14. Question 14. Which of the following condition would like to increase the drying rate in a batch dryer? So here is the answer question means conditions increase the drying rate in a batch dryers. First, the decreasing the air temperature, decreasing the air velocity, increasing the relative humidity of the air, and increasing the surface area of material to expose the air. So this is not possible here because of the drying rate, increase relative humidity of the air, and this is the increased surface area of the material exposed to air. So this is possible. So this is not possible. Question 15. Which statement is true about the relationship between the drying rate and the moisture content? So option given, the drying rate is independent of the moisture content, not dependent. The drying rate it increase as the moisture content decrease. This is also not possible because initially drying rate is high. After the sometimes, so drying rate also decrease with decreasing the moisture contents. The option C, the drying rate is a high static equilibrium moisture content. No, this is not possible. Option D, the drying rate is decrease as the moisture content decrease. Yeah, option D is the next. 16. Which of the following mechanism is primarily responsible for the moisture movement during the falling rate period? We already saw the mechanism is a different mechanism with a different from the rate period, like constant rate period and falling rate periods. So in the falling rate period is not diffusions. Now moving to the question number 17. In a batch dryer, if the drying rate during the constant rate period is 1.5 kg per hour per square meter, what would be the drying time required to reduce the moisture content from 30% to the 10% for the material with an initial mass 100 kg and drying surface area 2 square meters? So you have to calculate here time required to reduce the moisture content from 30% to 10%. So rate given, mass given, and area given. So here the formula to calculate NC is equal to 1 use this formula T is equal to WS by XI minus X T is equal to WS XI minus XF divided by A into NC. Here is a mass of dry solid. A is surface area, NC is a drying rate, X is the initial moisture content, X is the final moisture content. So you have to put a value here, you'll get the answers. 100 into Xi 0.3 minus 0.10 divided by 2 into 1.5, right? So T is equal to 6.6 hours. Moving to the question number 18. A batch dryer is used to dry 50 kg of wet solid. The initial moisture content is 40%. Critical moisture content is 15%. The drying rate during the constant rate period is 2 kg per hour per square meters. And the surface area is material 5 square meters. Calculate the time required to reach the critical moisture content. Okay. So here is a WS given. Here is a XI. Here is a XC. Here is a surface area. That's the A. Here is a NC. So you have to calculate the time. Means how much time required to reach the critical moisture content. So T is equal to WS XI minus XC divided by A into NC. Okay. So 50, 0.40 minus 0.15 divided by 2 into 5 at 1.5. Question number 19. A material with the initial mass of 100 kg and initial moisture content 30% is dry in a batch dryer. The drying rate during the constant rate period 3 kg per hour per square meter and the surface area 4 squares. So how long it will take to remove the 15 kg? So same concept here you have to use. Here W is given, initial given Xi. So here here area given here. Here is the NC given. So how long it will take to remove the 15 kg of moisture? Right. So here is a formula T is equal to Ws into Xi minus Xf, right? So here is the weight of the solid into moisture content. So if you multiply this, so you get a kg, right? So for example, initial moisture, then moisture 100 into 0.3, right? That's the 30 kg. And final is a 50 kg. So here is the final given 15, like here 100. So X is a 0.15. Put here ANC 100 to 0.3 minus 0.15. So we can directly we can write here 30 kg minus 15 kg, 4 into 3. It's a 1.25. So or we can write down is like 30 minus 15 divided by 4 into 3. 15 divided by 1.25 hours required to remove the 50 kg of moisture. 90. Question number 20. A drying operation is conducted in a material initially weighing 200 kg with a moisture content of 50%. After drying, the moisture content is reduced to 10%. If the equilibrium moisture content is a 5%, calculate the amount of moisture removed during the drying process. So here the weight given and their initial moisture content 50%. So after drying, the moisture content is reduced to 10%. So and here equilibrium moisture content given 5%. Calculate the amount of moisture removed during the drying process. So here initial moisture content, initial moisture equal 200 into 0. It's a 100 kg, right? And final 200 into 0.10 equal to 20 kg, right? So moisture removed equal to 100 minus 80 kg, right? So 80 kg of moisture removed during the drying process. Question number 21. A batch dryer has the initial drying rate 4 kg per hour per square meters. That's the ENS. If the surface area of material is 8 square meters, this is the A. The total moisture to be removed 64 kg. Calculate the time required during the constant rate period. Right? So T is equal to Ws Xi minus Xf by A into N. Right? So here is the total moisture will be 2 rooms in given the kg. So we can write down directly 64 divided by 8 into 4, right? So it's a 2 hour. So 2 hour required to remove the 64 kg of moisture from the solids. Question to question 22. A wet solid 30% moisture to be removed to be dried to 0.5% moisture in a tray dryer. A laboratory test show that it required 10 hours to reduce the moisture content of the same solid to 2%. The critical moisture content is the 6% and the equilibrium moisture content the 0.2%. The falling rate of drying is linear in the free moisture content. Calculate the time of the solid if the drying conditions similar to those in the laboratory test are maintained. All the moisture are expressed as per a cent of bone dry of mass solid. Right. So in this question, given xi given 0.3, right, and time required 10 hours to reduce the solid 0.2%. So xf so xf is a here is a case one first. xf is equal to 0.02, right? And x is given 0.06. X is equal to 0.02, right? Time given. So here we have to utilize this formula to calculate the time to solve these the problems. So in the case ones, so this is the formula. So xi given, xc given, a and c and w is not given, and time given. So all the parameters given. So first we have to calculate these terms in a case ones, right? So put the all the value in this equation. So you will get this terms of w is by a and c. So I already calculated. So w is a and c equal to 32.48. So now we have to calculate the time required to reduce the moisture from 30% to 0.5%. So required time of dry required time required for the drying from reduce the moisture from 30% to the 5%, 0.5%. So here for case 2, x f is equal to 0.005, right? So we know the this terms. Now just you have to accept value, you have to put all the other value the same. So you will get the times. So T is equal to 13.37 hours. So in this means here are the two cases. So first we have to calculate the first in the 30% to the 2%. So you know the we will get the these terms. After that in second case we have to calculate the time required to reach the 0.05% moisture. So is here is a time 13.37 hours required. Question number 23. A wet solid of 30% moisture is to be dried to 0.5 moisture in the tray dryers. Same or same? Okay, this is the same. Okay. In a laboratory drying trace of the granular hydroscopic wet solid, it took 8 hours to dry the solid from 28% to 2% moisture with a solid loadings 20 kg per meter square. Given x is equal to 0.1 and x star is 0.05. So this is equilibrium moisture and falling rate of drying being linear in the moisture content. All the moisture is on a dry basis. Calculate the time required for the drying the material from 25% to 1.5% moisture under the similar drying condition. What is the highest drying rate in the kg per meter square hour? Right. So it's a here the similar concept we have to use as a previous use. So first here the xi is equal to xf, right? Here is a w by a given kg per meter square, x given x star. So here we have to put in this equation. So we will get the in case one. Just you have to calculate this WS by NC 23.92. And case two, yeah, in case two, X is 25%. And XF uh, 1.5% means 0.015, right? So all the conditions same. So you put in this equation, you will get the times T is equal to 8.7 hour, right? So the highest here in this question I asked what is the highest drying rate. So the highest drying rate it occurs in a constant rate period. This ones, right? So WCANC equal to 23.92. So NC is equal to here W is by A. Here given 20 kg per meter square and 23.92. It's a 0.836 kg meter square per hour. Similarly, we can calculate the lowest drying rate in this falling period. Moving to the question number 25. Solid is dry, X is 0.32, except 0.003. The equilibrium moisture is a negligible and falling rate of the drying is linear in the moisture content. Calculate the critical moisture content of the solid under the particular drying conditions. if a given the drying time of constant rate period is the same as that of the falling rate period, and in a B case, the time by constant rate is a half that of the falling rate period. So here is a two cases. In the first case, so initial the condition given. So here is a TF equal to TC. Constant rate period is the same as the falling rate period, right? So these are the equals. So W S divided by ENC into XI minus XC equal to this term. W is by A, XC, X star divided by X into ln XC, X star, XX minus X star. So here is a the equilibrium condition negligible. So these terms get cancels. So XI minus XC equal to XC. This is also get cancelled. So ln XC by XF, right? So we have to calculate the XC, right? So XI given 0.3 and XF given 0.003. So put and calculate the XC with the help of the calculator. Calculate I already calculated 0.072, right? In a case 2, the constant rate drying is a half of that falling rate period, right? So Xi minus Xc equal to half of falling rate period. Xc ln Xc by 0.003, right? Here is a X here 0.3. So here is a Xc critical moisture content is a 0.108. So move to the next questions. The answer of the question 26 to 29 based on the below statements. Wet solids is to be dried from the 35% to 10% moisture under the constant drying condition in a 5 hours. If the equilibrium moisture content is a 4% and the critical moisture content is a 14%, and drying surface is a 0.0 meter square per kg dry weight. So means A by W is given, right? So the first question is to calculate the rate after drying. So here we have to calculate the ENC. But the whatever the moisture content given in the is given in the dry basis. Sorry, wet basis. So I have to convert into the dry basis. As we know, the calculate the moisture content under dry basis, kg of moisture content on a dry basis kg of moisture divided by kg of dry solid into 100, right? So here is a xi is equal to kg of moisture is here 0.35. So kg of dried solid. So 1 minus 0.35. It's the 0.5384. Similarly, XF This is a 0.15, 1 minus 0.10 equal to 0.11, and x star is equal to 0.04166, xc 0.1627. So I calculated here. So you have to put the value you have to calculate your like these ones. So here we have to calculate the rate of drying. So NC is equal to W x A into T x I minus xc, right? So here is A by W givens 1 by 0.03 into time 5 hours xi 0.5384 minus xc 0.1627, right? So NC is equal to 2.5 kg meter square into hours. So option C is the correct. Same statement. And the question number 27 is the how long it will take a dry the solid to 8% of moisture content at the same conditions, right? So here is the except 8%. So you have to convert 0.081 minus 0.08, so 0.086. So all the condition givens. So WSNC NC calculated now. So put all the value in these equations. So it will get time to means how much time required uh, to re, to reach 8% moisture. So T is equal to 1 by 0.03 into 2.5, just recently calculated from the last questions. Put the all the value here. Xi is this one's 0.5384 minus Xe is 0.1627, right? Plus X star given 0. Means we convert the dry solid weight basis into the solid basis 0.0416 into alien x my x all the value given here except 0.086. So time is a 6.5 hours. I already calculated 6.5. Option C is correct. Question 28. How long it will take the dry solid to 6% moisture content under the same conditions? So here is the except just like 0.06 1 minus 0. Convert into the dry basis 0.063, right? So the same formula you have to use calculate the time. So 7.72 hours. Option C correct. So moving to the last question of today's sessions. So how long it will take to dry the solid from 20% to 6% moisture content if the initial moisture is at 35%? So here is a given the initials 20%. So it is on a weight basis. So we have to calculate in the diabetes. So xi equal to 0.25, right? Xf is equal to 0.1628, and NC calculated in the first questions of this statements 2.5 kg meter square per hour, right? First, we calculate 22. So T 22 6%, right? Equal to T 22 14% plus T 14 to 6%, right? This is the question. This is the equation number 1. So time required for 22 14% calculated already 1.16 hour, right? This is a 2. Now we already calculate the time required for 35% to 6% is a 7.78, right? And time required for T 35% to 14 is a 5 hour, right? Now T 35 to 6% equal to time required by 35% to 14% plus T 14% to 6%, right? This is the question, equation number 3. So here the time required 35% to 6% is a 7.7 day, and time required 35 to 14% is a 5 hours. So you will get the time required by 14 to 6%. So here is the time required 14 to 6%, right? Is equal to 2.78 hours. This is a 4. Now put the value equation number 4 and in equation 1. So we'll get the time required for 22 6% equal to 1.16 plus 2.78. That's the 3.94 hour. Option B is correct. So I'll cover all the question based on the this week's topics. So if you anybody have a doubt about any doubt about the regarding any concept or any questions, please ask. Okay, we don't have any questions, so I conclude today's sessions, and we will meet on our next Friday on next topics on the upper drawings. Thank you.